Hi friends, I'm Yugen. Welcome to my YouTube channel Interesting Quantum. In this video, we are going to see the complete wave function and how to normalize it, that is, the normalization, through one example. Now let's start with Schrodinger's time-dependent wave equation. IH cross dabba by dabba t of psi, which is function of position as well as time, is equal to minus h cross square by 2m del square psi plus v psi, where v is also position and time dependent. IH cross dabba by dabba t is Hamiltonian operator. Del square is the Laplacian operator and its value is dabba square by dabba x square plus dabba square by dabba y square plus dabba square by dabba z square in 3 dimensions. If we are dealing with one dimension only, we can choose any coordinate between x, y and z, but conventionally we choose only x coordinate. Then minus h cross square by 2m del square is kinetic energy operator and v is potential energy operator. So let's say this Schrodinger's equation as equation number 1, and the solution of equation 1, let's say it is phi 1. So above equation 1 can be written as IH cross dabba by dabba t phi 1 is equal to minus h cross square by 2m del square phi 1 plus v phi 1. If I multiply by a1 on both sides, which is complex number, we can get a1 IH cross dabba by dabba t phi 1 is equal to minus a1 h cross square by 2m del square phi 1 plus a1 v phi 1. I can put a1 inside the derivation, that is because it is independent of time as well as position. I can say a1 phi 1 is also the solution of equation 1. Similarly, if phi 2 is another solution of equation 1, then I can write equation as this, and again on as similar way I can write a2 phi 2 is solution of equation 1. So there can be n number of solutions like phi 1, phi 2. So in more general case I can write psi is equal to a1 phi 1 plus a2 phi 2 plus so on. It can also written in matrix form as like this, where r1 r2 up to rn are number of coordinates and phi 1 phi 2 up to phi n are different solutions. Now we will see what is the normalization. Basically it is mathematical process. The formula for probability is given by integration over x1 to x2, or generally we take it is minus infinity to plus infinity psi star psi into dx. So if this probability psi star into psi dx is equal to 1, then we call psi is a normalized wave function. So what does this mean? What is the necessity of normalization? So basically the normalization is needed to get the complete information about the wave function or that particular case. So if I am getting probability 1, this means the probability of finding that particle in that certain volume or area is 1, means I can get the particle inside the box for sure. It cannot get outside the box. But let's say the integration is 0.2. What does this mean? This means particle can be outside of the box. It is not under consideration. It is not under observation for 0.8, or we can say 80%. So this means we should increase our area of analyzation or our area of observation so that we can study totally, completely about the particle. So the normalization is basically to multiply the wave function by certain number to get probability equal to 1. So let's multiply in this case by 5. Multiplying by 5 on both sides, we can get probability is equal to 1. So in this case, root 5 is the normalization constant A. Let us suppose another case. If the integration is 2, can probability have value is equal to 2? What does this mean? So basically this means we are analyzing the volume, we are analyzing for greater volume. We need not to analyze, we need not to observe such large volume. So to deduce this to certain value, we multiply 1/2 and we get probability is equal to 1. So in this case, the normalization constant is 1 by root 2. Now let's consider one example. We will solve one example. This is very simple because it is in one dimension only, that is x coordinate. So the wave function is ax by a, where x lies between 0 and a. If it is between a and b, the value of wave function is capital A into b minus x divided by b minus a, otherwise 0. So let us first draw the wave function. So this is our graph. In x coordinate we are drawing x, that is position coordinate, and y coordinate represents the wave function. So for first case, from 0 to a, it is linear, as we can say y is equal to mx plus c. So phi is equal to a by a into x. So m is a by a and plus c. C is 0 in this case. So it is just straight line and slope is positive. So it is increasing. From a to b, this is also linear case, but in this case slope is negative, and this is the nature of our wave function. So at value x is equal to a, we have the most probable value. You can see the value of phi is greater at a. Similarly, we can get probability at a greater. That's why it is most probable value. So we will try to normalize this wave function. In this case, normalization is just getting value of capital A in terms of small a and small b. So let's solve. We have formula integration psi star psi is equal to 1. So in the next step we will put our given wave function. It is split into 3 different limits: 0 to a to b, and any other. Means minus infinity to a, the integration is 0, b to plus infinity, integration is 0. So we have taken only 2 integrations. So we just put the values of phi, values of psi, and this becomes, so capital A and small a is constant. By solving we can get further equations. B minus x bracket square I have solved, and then we can get integration. Putting the limits we can get this value. Further solving we can get this value, and if you solve further, this is a square b by 3. So this must be equal to 1 for normalized wave function, and if this condition should be fulfilled, we should have the value of a is equal to under root 3 by b. So in this way we have normalized the wave function, and this will give the complete information about the particle associated with the given wave function. So enough for this video. In next video we will watch and we will solve another examples, and thank you for watching. Like, comment and share, and if you have not subscribed yet, subscribe it and press the bell icon so that you can get further notifications. Thank you.